I was asked to give a talk, not now, but in about 6 months' time, on comparing uncertainty mitigation in 3D modeling in the mineral space versus how it's done in oil and gas. And so you're the guinea pigs for this ramble through this question as to how different types of scientific or geoscientific scenarios are treated in terms of uncertainty. And I'm sure you all are aware of who Dory is and who Nemo is. If not, the only thing you need to know is that Dory has got terrible short-term memory problems and Nemo doesn't. We'll come back to that at the very end. Why are we talking about uncertainty? Because it matters. It can have scientific and/or economic value. And the way I try to convince my audience of this is that we might, for example, collect a sample of granite, date it, and we might have spent $5,000 on all the acquisition and crushing and sampling and human time. And $5,000 for a nice date is quite nice. But what happens if I now tell you that the age of that was 107 plus or minus 290? Then you're going to go, I really don't want to spend more than about $50 for that sort of information. And so it's really the pluses and minuses that have the value much more than the age, or at least they're intimately combined. And if I tell you that it's 107 million years, but I actually don't know the age, then you go, well, I don't know what the value of that information is, but it's clearly somewhere between $50 and $5,000. And it's the same for 3D geological modeling, except in 3D geological modeling, in most cases, we're down here. We make our 3D geological model or our geophysical inversion, and the error bars are actually very hard to define. So what we're going to go through at a breakneck pace is looking at uncertainty. And here we have a whole series of different papers referring to uncertainty, some of the very beautiful, elegant summaries of divisions of how uncertainty builds up in a system. But mostly they're treating different parts of the problem individually and just categorizing them. And what I'm going to do here is look at 3 specific scenarios that are different. Geologically different. They're different because the types of data are different. They're different because the types of questions we want to ask the data are different. And so the first example is sedimentary basins, where we have lots of nice 3D seismic. As far as I'm concerned, they're relatively simple in terms of their structures. There's lots of software that people use for that, Petrel and all sorts of other things. The starting point for the model is probably the 3D reflection seismic cube. And essentially, in terms of dimensionality, you're going from 3D to 3D. So things are pretty good with some limitations. If you're in the mine space, you've got lots of borehole data. The geology is very complex. There's lots of dedicated software. There's lots of different types of data available. But it's essentially a 1D to 3D transform because you've got boreholes. You've got lots and lots and lots of boreholes. But essentially, you're using them to make your 3D model, and everything else is subsidiary. The fact that the boreholes are going in all sorts of directions helps you, but you're taking information from a very small, thin line in space and then extrapolating out. At the regional scale, they're very complex situations. The 3D constraints are rather poor in comparison. Typically, just most places, it's the geology map of the surface, gravity and mag. And anything else is only partial or 2D. There isn't much software dedicated to it. The primary starting point for most 3D geological regional settings is the top surface of the geology. So it's essentially a 2D to 3D transform. And I won't worry about the lithosphere here, except to say that it's another class of types of data and questions. Again, it's typically a 3D to 3D transform. And of course, there are lots of other reasons that people make 3D geological models with different questions, different data sets, and so on. But when you actually look at them, the actual model building process typically reduces to something like this. And this is a paper from 1990, so a while ago. But they'd already worked out that basically it was a 2-stage process. You make a discrete model which is dividing up your geology into heterogeneous large-scale domains. which are the building blocks, and then within those domains you have some sort of continuous variation of properties. And that's still how people generally make predictions about behavior in 3D today. You make in the mind space, you talk about domaining your model, so you have different domains which behave within those domains in some sort of consistent fashion, but when you go from one domain to the next, there may be significant changes in behavior. So that's the sort of the two-stage model. When you actually go a bit further, we can get this sort of nice path, because we've got the domain construction and then property infill, and then you use that property infill to make some sort of downstream prediction, which is going beyond just the fact that I've got some sort of petrophysical model of the Earth now. We're actually converting that petrophysical model into rock physics, so porosity, or into prospectivity analysis, or whatever you want to do with your 3D model. And there's all sorts of steps before that that we can't ignore, because even though they're not really part of the model building process sensu stricto, they're actually inputs into the model building process. And so we have this nice wandering path that we're going to look at, uncertainty in all of these different areas. Now, of course, in the real world, we don't have this nice wandering path. We have some sort of path like this, where we start off somewhere, and then we go back and we collect some more data, and then we start to bring in some inversions. And it's not this nice linear system, but we're going to keep it linear just so that the conversation flows a bit more easily. So we'll start off with measurement error and natural variability. This is some work that was published last year, where somebody took a slab of sandstone and they took 30 measurements of the sandstone with the same compass, and then they changed compass, took 30 more measurements, changed compass, took 30 more measurements, and plotted them up on a stereo net. So they plot up here. And you can see this is essentially just a measurement error. So even if you measure the same thing 30 times, you're getting a 6-degree error in terms of these different systems, and the different colors are because they were measured by different instruments, so the same person using different instruments gets an error. And this is equivalent to sort of all the different errors that you have when you're collecting geophysical data. They're quite easy to characterize once you've done this sort of analysis for your own machine, of course, and you can build that into any assumptions about the unknowns of what's going on. Natural variability is something quite different. In natural variability, we have a crack in the surface of the Earth, and we can map it out at some particular scale. And we can see that at this particular scale, there's quite a large variation in orientation, just in something that, of course, we can see in our eyes has got a very similar general trend. But if we say that this isn't the surface of the Earth, but this is a cross-section, then where we measure this is obviously going to result in a quite erroneous idea of what's going on. So this idea of natural variability of what's going on beneath the surface, especially at the regional scale, is really important, because it doesn't matter how well you've mapped the surface, God knows what's really going on down there. And so, of course, we put in boreholes, and that's something that's very useful because it actually does tell us what's going on down there. This is a paper looking at measurement while drilling. So they've looked at the source errors in terms of understanding the variability in the Earth's field, which is what they use, Earth's magnetic field, which is what they're using to work out where the drill hole goes. And at 2.2 kilometers, they're getting an error, positional area of where the drill hole is, of something like 60 to 100 meters in east, west, north, south, and 15 meters in Z. And so these are fundamental errors that are going to build into whatever geological model that you're going to be making. And of course, if you're looking at this in the mind scale, they don't tend to be 2 kilometers long, although in South Africa they might be, but in most places they'll be much shorter. But they also don't tend to use this sort of technology to work out where the drill hole is going. So the fundamental error associated with a 200-meter drill hole might still be 10, 15% of where you think it is, and that all is obviously going to feed into the uncertainty. And this is the work of Evren Pakius-Charrier, who's been looking at, these are all different simulations of where a drill hole is going at depth, because there is an inherent uncertainty in the measurements that have been made. There's also, of course, natural variability in the petrophysics. And so this is some work from Nick Williams from the Yilgarn, looking at just measuring density versus susceptibility. So we had this in the previous talk, this idea of whether we could correlate susceptibility and density as a constraint on our inversions. And we can see that, well, clearly the massive sulfides are behaving very differently in the ultramafics, but everything else is just sort of splopping on top of each other, which means that using it as a constraint is going to be quite limiting. It's interesting because there was, at the AEGC, there were two different talks by John McGaughey and by Mike Dentith, looking at, based on their quite extensive measurements of petrophysics, one in Australia, one in Canada, they came up with diametrically opposite opinions as to what the most important control is on petrophysics at a regional scale. In John McGaughey's vision, there's fundamentally a lithological control which is modified slightly by alteration, and Mike takes the completely inverse view. So even something as fundamental as what the controls are on density and susceptibility in these systems is still up for grabs, and it suggests that there's probably more work needs to be done in that area. So we've got measurement areas, natural variability, so positional measurements of 5%, structural measurements plus or minus 5 degrees. And we could probably mitigate this, and in fact that's some of the work we've been doing, by stochastic modeling of the measurements that we make and saying, okay, this observation isn't a perfect observation, we're going to replace it by a probability density function of observations with some sort of error. The errors resulting from natural variability are much harder to mitigate because we can't measure beneath the surface, and that's really where the problems are coming from. So we could perhaps mitigate it partly by having denser data collection at the surface, so we get a better feeling, so whatever's going on the surface, we can at least project it down further. But again, we're going to come back to stochastic modeling as we are in most of these examples. If we look at our observational uncertainty, here's a nice example of two maps of the same area. It's from southeastern Côte d'Ivoire, Ivory Coast, one by the French Geological Survey in 1992, the other by the German Geological Survey in 2004, and they give a different answer. They're not completely different, but it's sort of a point of pride that I can look at any map in West Africa and I can tell you who mapped it, regardless of where it's from, regardless of which country it's from, because they have a house style. And the house style for the Geological Survey, the German one, is that they have things that are going along and then they're cut by perpendicular faults. Whereas the house style of the French Geological Survey is that things lens out. I'm not saying one is right or the other is wrong. I have no idea. I mean, there's not that much outcrop. But they're quite different solutions to the same problem with fundamentally the same data. I know that the German Geological Survey used the MAG data. It was available for the French Geological Survey. I don't think they used it. But that's part of it, is what do you choose to use as data sets, as inputs. Since at the regional geological scale for 3D modeling, the geological map is the fundamental data set that you start with, it's kind of important to accept that the map is just another model, and in fact suffers from all the same problems as our 3D model, except that it's one of our inputs to our 3D model. So it's got its own ambiguities that we have to somehow accept. Even the positions of these same contacts are quite different. Of course, if we're logging, if we're all familiar with the things that look like this, where if you're very lucky, you know what all the letters mean. If you're not so lucky, you just know that they're different. And the key, of course, is to take one log from one place where we've got all these different properties and to try and correlate it in space with other logs. And that's quite hard. And of course, it's, the oil and gas industry has been doing this for a very long time, and it's just starting to become more widely used. And this is work by David Nathan from UWA, where he's using gamma logs to identify particular shale horizons and then correlating them between different well holes, drill core in this area. So this automation of this process is not something I'm going to talk about, because you've probably heard 50 talks about it before, but it's certainly one of the major areas where, for example, the MinEx CRC is doing work on trying to increase the amount of information we collect going down the hole so that hopefully we can correlate it between holes. And so in terms of observational uncertainty, the mitigation is partially coming from additional data types, so things like gamma logs that we haven't traditionally collected in the past, and partially coming from numerous different machine learning approaches that are trying to extract the log automatically. We talk about interpretation ambiguity. That's always a fun one. This is possibly the most boring bit of geology on the whole planet. It occurs under London. It's a number of different rather boring sedimentary rocks that are more or less horizontal, and there's tons and tons of drill core that goes through different parts of it. And this study by Lark et al., they took 28 different geologists, gave them exactly the same data, and asked them to make an interpretation of this red dash surface. And the blue lines are the 95% confidence limits, and the red line is one particular geologist's interpretation of where that layer was. It's not a particularly complicated layer, but you can see that there's quite a lot of variation when you consider that there's about plus or minus 7 meters of uncertainty in the 95% for something that's only 17 meters deep. So something as simple as that, something where there's as much data as that, when you give it to 28 different geologists, you get, of course, 28 different answers. And so we'll talk about what to do about that a bit later on. Of course, one thing that's happening more and more in the mine space is that they're taking up the technology of oil and gas, not just in terms of logging, but in terms of 3D seismic. So this is the 3D seismic of the Darlot-Centenary gold mine. It was from the AGC conference this year. And it's kind of tragic that at the end of spending quite a lot of money and some very, very clever people doing inversions, you still end up drawing lines on these stupid things in order to make your geological interpretation. But that's where we are, and it's the same in oil and gas as it is in minerals, is that fundamentally you get something like this, and as beautiful as it is, you're reduced to drawing lines on it. And in the same logic as the example from the London clay, here we have a synthetic 2D data set that's been forward modeled to produce our seismic data. And this is the work of Claire Bond, where she gave it to 20-odd different interpreters with different backgrounds, some of them professional, some of them amateurs, all of them with some experience in working in this area, though. And so this is one synthetic interpretation where they're 200% confident they got the right answer. But here's some other ones. And they were all variably confident as well. And when you actually look at it, there's inversion, there's extension, there's thrust, they didn't know, there's diaphorism, strike slip. So every interpretation under the sun is coming from this same synthetic seismogram where we actually know what the answer is. So interpretation and ambiguity is a killer in not just in oil and gas, but as I showed you before, in the hard rock seismic, it's going to be even worse because the quality of the signal we're getting out is much, much worse. What are we going to do about this? Well, what we can do is we can try and quantify the quality of the signal where it's been interpreted. And this is the work by David Nathan and Jason Wong from CT. And so this is magnetic data, and they've extracted various different signals from it in terms of the local texture of the signal, where the strength of the ridges are, the strength of the valleys, the strength of the edges, and provided that with use that to quantify the quality of the signal for different interpretations. And I forget who did this interpretation. Was it you or Vashek? It was you. So it's Mark's interpretation based on the same data, and where it's green or red, it's saying that this software agrees with or thinks that there's very good evidence for these signals, and where it's blue, it means that it's weaker. But Mark was using his brain, whereas this software was only using 2 or 3 different aspects of the signal. So there's quite a lot of work to extract Mark's brain and put it into the computer, but this is the direction that we're going in anyway. Of course, as I alluded to before, when you've got drill hole data, logging it is great and is absolutely fundamentally important, but it's not the whole story in 3D. The whole story is joining up the dots. And you can take the same data, and this is a cartoon from Guillaume Caumont from the GoCAD group in Nancy, and you can join it up in many different ways. So perfect logging does not give you perfect 3D models, but it certainly improves your 3D models. They're all based on the same drill core data. And how can we improve this problem of subjectivity? There's a nice paper by Curtis and Paulson and Curtis where they did one of these experiments where they gave people seismic data and they asked them to assess the probability of there being a reservoir, a seal, and a fault. And before they went in, they had a particular variation of ideas about these probabilities. As they came together as a group, they came to a decision, and then after they left the room 5 minutes later, they started to change their mind again. But there's this idea that maybe if people do this work as a group rather than individually, then you can actually reduce the subjectivity of the problem. And there's this quote from this paper saying scientists should not be ashamed of subjectivity, but we do need to find ways of quantifying it and reducing it, and that's what we just saw in the work by David Nathan and Jason Wong. And I think I've got that slide in again. Oh, no, I've got them in the wrong order. So collective analysis might be the best way of reducing uncertainty as a result of interpretation ambiguity. In terms of inversion, I'm not going to give you a talk on inversion since we've just had a talk on inversion, but I will emphasize this, that most, if not all the time, geophysical characterization and subsurf involve estimating solutions to ill-posed inverse problems, which means there are multiple solutions that will fit the data. And in the oil and gas world, this means that people are actually producing depth uncertainty maps. So this is a depth uncertainty map. If you can't read it, that's 120 meters and 40 meters. So that's the variation in uncertainty at a particular horizon. And so that this is actually being quantified. So, and this uncertainty here is coming from the 3D velocity modeling, which is kind of a black art in the oil and gas industry, where there are procedures to do it, but as you get to more and more complex terrains, there's more and more uncertainty associated with this velocity modeling, but at least it is being characterized in the surface depth. Of course, when you have inversions of gravity data, and this looks rather like a slide I just saw, you can play the game of just saying there isn't one answer, there are multiple answers, but then it's much more difficult to know how to feed that into your geological modeling process. And, but it's certainly something that we need to be working towards. So some sort of simulation or variation in the properties is definitely needed. In terms of domain construction, we get to all sorts of new problems. So now we're talking about defining in 3 dimensions those sharp barriers. They could be faults, they could be stratigraphic horizons, they could be salt layers, they could be whatever you want, where there's fundamental changes in properties across these sharp surfaces. And one of the problems that we have is to do with scaling. Whenever you make a 3D model, geological model, you're simplifying the real world from whatever your data sets are. You have to. We don't have enough data to make as dense a model in 3D as our drill hole variations, as our geological map, as our seismic data. This is some work by Watterson from 1996, where he mapped out a wave-cut platform, all the different faults, and then he just extracted the faults where the throw was over 20 meters, because these are the ones that you're going to be able to see in seismic data. So essentially, your seismic data is sampling, is going to produce, at best, if it's done perfectly, a map like this, whereas the original data was much, much more complicated. And so in terms of trying to predict property variation, obviously we've got a problem there, especially if we're looking at transport properties or something like that, where the faults are important. One way of dealing with this uncertainty is by stochastic simulation, and this is Nicolas Sherpo's PhD work, where he took a whole series of seismic pics of where faults were in a series of parallel lines, and then said, well, I actually don't know which fault joins up with which fault because I don't have any information in between. So he did a series of simulations, so the faults are in exactly the same place in all of these models. There are these black lines here, but where the connectivity between the faults was, he allowed to vary. So this is a way of allowing you to create multiple hypotheses for what your domaining is that you can then worry about later on how to use that. The same sort of work is being done at Monash at the moment by Lachlan Gross, who's just finished his PhD? Yeah, I think he's just finished. Where we're looking at isolated fold information and running simulations to produce 3D models of this folded system based on the knowledge that this is actually undersampling what we need in order to produce a unique solution. Therefore, multiple solutions are valid, and therefore multiple 3D models can be generated from this. And I'm not going to go into more detail on that. And then finally, the last thing is that all geological modeling software, somewhere or other, has some sort of interpolation scheme or implicit surface generation scheme, which is based on something nice like co-kriging or radial basis functions, something nice and mathematical that is tractable for the computer to solve the problem, but doesn't really have any basis in geology. So why you choose a radial basis function A rather than B? Meh, because you like it, because it solves quicker, because it gives you a decent smoothness to your answer. But there's no geological reason for choosing it. It's just mathematical and personal. So you can play around with that uncertainty with changing the interpolation scheme, and you will get a different answer. This is some nice work done by Eric de Kemp and his group from the Geological Survey of Canada, where he shows the same geological model, and I've forgotten completely where it's from, but Canada, from 2010 to 2015, and he shows various different models. And at the bottom here, he's showing the data availability that went into making that model. And here we have colors which are distance to drill hole data. So red means you're far from the data, and so those dots are the drill holes. And here, distance to the map traces that we use to build up the 3D model. And he's come up with this plus this equals some sort of favorability scheme where red means we know more and blue means we don't know so much. But what he's also done is that he's worked out the uncertainty by combining all of the different models over a 5-year period. And here, red means low uncertainty, so we know what's going on, and green means high uncertainty, which means we don't know what's going on. But what's nice is that there's actually a pretty good correlation between where the areas where we know what's going on and the favorability as defined by where we're close to the drill hole data and the outcrop information. And this is similar to some type of work that Alan has done in the past, looking at what is the actual amount of data we have in a field area that we can use, and therefore how sensible is our interpretation going to be. So with domain construction, the two biggest problems are major personal bias. You draw the lines where you want to at that stage. And in the case of oil and gas, there's also the problem with velocity model uncertainty, because that's going to shift your whole model. It's basically, it doesn't change the topology of your domains, but it changes where they are in real space, which is obviously important. And so again, we can mitigate that by stochastic simulation, but again, perhaps by increasing the number of different data sets that we're using to solve the problem. We get to property infill, and in the mineral space, the classical property infill is some sort of kriging, some sort of geostatistical approach where you throw in all your drill holes, you throw in whatever you have, you press the button, you do all sorts of pre-processing of that data to make it all nice, then you press the button, and it'll make some sort of geostatistical estimate of the distribution within a single domain. As soon as you go to a different domain, then you want to redo the calculation again, because you're saying that these things are only stationary in a geostatistical sense within a particular domain. There's no physics behind any of this. This is just a purely geostatistical approach, and that's probably reflecting the level of knowledge we have about the complexity of the situation. If you go to oil and gas, there's many more physics-based approaches to property infill. So people are looking at simulating, at least in a conceptual sense, river channels and variations in porosity and permeability associated with graded bedding, all these sorts of things that are based on our geological understanding of what the system looks like. It would be great if we could do that at the regional scale, at the mine scale, but I think it's fair to say that we don't actually understand it well enough to do that, and that the mines, the lucky thing about most sedimentary basins is that, especially to somebody that knows nothing about them, is they all look the same. If you go to all the mines, they all look different, and they've all got different mineralogy and different amounts of alteration and overprinting and structural complexity, and so there isn't, we're kind of stupid in that we haven't developed that physics-based understanding that we're going to need to match this. And to show you the sort of extremes that you can go to in river channels, this is some beautiful work that came out last year. The blue line is an actual river channel as imaged in Seismic, and what they've been able to do based on physical simulations is to calculate where that river used to be. So by understanding enough about how meanders evolve, they've actually gone backwards in time and said, this is what it looked like at t-1, so doing a backward inversion of what the river, how it's evolved as a function of time. And then, of course, they can compare that with the seismic data to see how it's worked. And, of course, I mean, you know, the further back you go in time, the worse it gets and the less likely it is to look like anything. But it's that level of sophistication that we're just nowhere near that in regional geology or at the mine scale. So stochastic simulations, but incorporating prior knowledge, prior geological knowledge, even if it's not geophysics, even if it's not physical or chemical, we do know things about mines. We do know things that go beyond just a purely geostatistical approach, but for the moment, that type of information isn't really used. And I'm not going to talk about downstream prediction because it brings in all sorts of other worlds of pain, because each of these predictions in itself involves a whole series of assumptions that need to be made that are very specific. So if we're talking about rock physics or geometallurgy or porosity, we have to do some sort of transform between the petrophysics that we could measure and the porosity that we couldn't measure. And again, in oil and gas, this is done routinely, but in the mineral space or in regional geology, we don't have that sort of understanding yet, or at least people haven't tried very much, let alone if we're getting down to things like economic viability. What we really want to be doing is doing all of this at once, I guess. So let's look at where we can do multi-stage uncertainty propagation. And again, this is from that same paper in 1990, where they were already thinking about how to do multi-stage uncertainty propagation, where we have a whole series of different aspects of it, so permeability, aquifer size, parameter interdependence, that for each one, they can come up with a probability density function and then combine them all to produce one estimate of the behavior of whatever it was that we want to predict. And we can even go to the stage of including the economic uncertainty to come up with predictions of net present value and all the different variations in likelihood of something far down the track. At the moment, we're far from being able to take our raw data all the way through this process. Again, back in 2001, this is the sort of idea of how you might be combining these uncertainties. We've got the uncertainties from picking horizons and faults, the uncertainties from the sparse 2D data, the uncertainties related to time migration, and these are all combined to produce a global uncertainty which you can then use to assess the likelihood of finding anything. And what you do with this information, well, that's up to you, but this is two different ways of looking at it. One, we could make the best image that we can and then drill what we want. An alternative is to make the best image we can and to drill where we know the least. And that's going to become particularly interesting, that question, when we look at the MinEx CRC and the National Drilling Initiative. Because the National Drilling Initiative, which has now been funded, is going to be trying to decide what is the best drilling strategy to optimize cover and bedrock sampling. So we're going to be putting lots and lots of new holes in the ground, but we want to know lots and lots of different things from each well. We want to know what the character of the cover is. That could be regolith, or it could be a sedimentary basin, it could be anything you want. But we also want to know what's at the bottom of the well in terms of the basement. And so optimizing that strategy means that we have to think about different ways of drilling that have ever been done before. And this diagram here, which this is from the Mount Isa region, showing where they could drill effectively offshore Mount Isa in the neighboring sedimentary basins, it's not going to be done on a regular grid. Well, at least I don't think it's going to be done on a regular grid, because you would imagine that there's a better way of doing it. What that better way of doing it in is something that we're going to have to learn within the scope of the CRC. The work that Jeremy's been doing, Jeremy Giraud and Evren Paquet-Charrier from UWA, feeds into those sorts of questions, because it's looking at how we can build geological models which have an inherent uncertainty. So that's a geological model of Mansfield in Victoria. This is the uncertainty for lots of different lithological units. And this is what Jeremy did. It's been published now, taking, in this case, in a 2D section, looking at the starting models and adding different amounts of information. First of all, adding petrophysical information, but not just point petrophysics, but petrophysics with a probability density function, and then adding the uncertainty from the geological data, because we don't have a single model, we have multiple geological models, and then combining them finally to getting to a geophysical inversion, a joint geophysical inversion of, I'll get it right, magnetics and density, combining the petrophysical uncertainty from the petrophysical PDFs, combining that with the geological uncertainty by running hundreds and hundreds of geological models to produce something that, is pretty good in terms of the overall recovery of the initial model. Of course, you need to have good petrophysical data, and you have to have enough geological data to even be in the ballpark. One of the problems with that approach, which is being attacked by Evren in a paper that's going to come out soon, hopefully, is that the geological models that result from our uncertainty in all of those things we've talked about so far aren't continuous in their behavior. They're discontinuous in that they're classes of one type of model that have very different behavior than a different type of class. And this is the way we're attacking this problem is by looking at the topology of the models. And I'm not going to go into a gory description of topology here, but it's just we're looking at, for example, whether this unit here is touching, the green unit is touching the blue unit across a fault. And we can see in some of the models it does, and in some of the models it doesn't. If you're looking at any sort of transport properties, this sort of connectivity is fundamental in determining and be able to predict what's happening in this system. So what he uses is the topology, and we use these adjacency matrices that I'm not going to describe here, to come up with a series of classes that say, well, yeah, I made 1,000 models, and yes, there is variation, but fundamentally there's 4 different types of models in terms of their topology. And so what we now have is, instead of a continuously varying set of models, we have 4 classes of models with different properties. And so with that, we can come up with 4 different, in this case, 3 different examples where we have 3 different patterns of uncertainty. So 1 means it's very certain, which is red. 0 means it's very uncertain, which is blue. And these are the 3 topological classes. And when you're in areas where there's a lot of agreement, they don't vary very much. But when you get into these areas with the maximum complexity, you can see that they're quite different predictions in terms of the uncertainty. And so at one stage, we'll be needing to generate our geological models, but then also classify them rather than just mushing them all together again and getting one uncertainty, which is the type of work that's been done up until now, because you're missing lots of information if you do that. So there are various different strategies that people have tried for carrying uncertainty through this different process. Remember, the first thing I showed you was a measurement of the orientation of a sandstone layer. We want to be able to retain that uncertainty all the way through the process into our final geophysical inversion, because like any probabilistic system, you have to accumulate the probabilities. You don't just take one and throw it away when you don't like it anymore. So one way you could do that is by some sort of brute force Monte Carlo stochastic approach, where you basically just did gazillions of different models. But that's probably going to tax even the nicest computers. So we probably need to do something. And up until now, and the work that I showed you from 1990, this idea was that, well, if we can characterize the uncertainty in terms of probability density functions, then we can feed that into the next stage. And then each stage, you only have to carry the probability density functions of the cumulative set of models that you get into the next set of the next stage of the process. But what that leaves out is this idea that there may be fundamental classes of behavior that we want to retain, because in the end, one of the things we build our 3D models for is to produce hypotheses. And if we can produce a class of 4 or 5 different geological models as n-member hypotheses, it then becomes much easier to understand how to test the hypotheses. Because then you say, well, if I drill here, I should expect to see this. Whereas if you take a single model or a single fuzzy set of uncertainties, it's much harder to extract what that key test will be for the model. So we can mitigate it by we can mitigate the compartmentalization of everything by having better propagation strategies. So just to sum up, the different types of approach to 3D modeling that occur in mines, basin, and regional modeling, they're different key sources of uncertainty. It's not the same in all of these systems, and therefore, if we want to improve our understanding of a model at a regional scale, we're going to have to try and address some problems. Probably they're more important than others. Throwing money is always a good solution. Throwing money at a problem. If you could do 3D seismic across the whole of Western Australia, we would solve lots of problems, but not the budget of Western Australia. So what's stopping us? I'm not going to go into detail in this, just saying that fundamentally what's stopping us from doing this sort of work right now is that the software we have almost never takes uncertainty as an input. You can give out uncertainty, you can make 1,000 models, but none of the standard software that we use for building 3D geological models uses the uncertainty in the structural information, uses the uncertainty in the fact that there's variation in geophysical models that might be constraining it, using positional uncertainty in drill holes as an input to your modeling system. They're just something that you take the best model you can, the best drill hole position that you can guess, the best estimate of what the property is, and you put that in because that's all the systems will allow. They don't really allow physics-based prior knowledge. So in the oil and gas, yes, you can do fantastic simulations of river channels in minerals and at regional scale. We're just getting to that point to be able to say something about folding, which is more than just a simple kriging of the data. Topology is only partially used in most of these systems. And even in oil and gas, typically, once you've set up your structural framework, you do all of the games within those fixed domains. So they're not simultaneously playing with the domain boundaries and playing with the property infills within those systems. So, of course, we've got the solution, which is to start again, and that's what we're going to be doing now with the Loop Consortium led by Laurent Taillère out of Monash. And we've got funding from MINEX CRC that's going to feed into that, and the Geological Survey of Canada's also funding some postdocs in that. So we're up to about 6 postdocs that are going to be working on this, using a lot of the work that I've already shown you in one way or another. So there's a lot of what I would call prototype codes that they work, but you wouldn't want to give them to anybody. So these are now going to have to be incorporated into a single system. So it's a large consortium that's going to be working on that. And so basically the punchline here is that the problem that we have at the moment with dealing with uncertainty in regional geology and at the mine scale, but even to a certain extent in the oil and gas space, is that we're very good at characterizing uncertainty in any one of these different areas, but we're very bad at propagating the uncertainty through the entire model building process. So we end up with a system like this, where we do something really clever, and then we forget about it, and we just give the best model to the next system. We do all sorts of fun games with inversions, and then we say, okay, here's the one you're going to interpret. We do interpretation, and yes, of course, it could have been this or it could have been that, but we give you the interpretation that we think is the best one, but we've thrown away the possibility that it might have been 40% that, in fact, another model was correct. And each time we're forgetting what's gone on before, which means that we're going down a very tortuous path, which is this whole path, where each time we're saying this was the best model, and therefore we've applied that to the next stage, which was the best one, we've applied that to the next stage. And really what we need to be doing is coming up with a coherent workflow where the uncertainties are attained and propagate from data acquisition all the way through to model predictions. And we're a long way from that at the moment. But that's where we're going for the next 10 years. And this is probably pretty much how you feel right now. Thank you.